Welcome to the precipice of understanding, where reality itself begins to fray at the edges. I'm your guide today through the labyrinth of the universe's most baffling propositions, the strangest theories in modern physics. What you'll encounter in the next 30 minutes may seem like science fiction, yet these concepts emerge from the same mathematical frameworks that gave us smartphones, GPS, and nuclear energy. The difference: these theories operate at the frontiers of comprehension, where our everyday intuition crumbles into cosmic dust. Imagine a world where cats can be simultaneously dead and alive, where your mere observation of a particle determines its past, where invisible strings vibrating in dimensions we cannot perceive form the fundamental fabric of existence. These aren't hallucinations or mystical pronouncements. They represent our best scientific attempts to explain the universe in its most fundamental form. And the most perplexing revelation of all? These theories work. Their mathematics produces predictions that match experimental results with stunning precision. To begin our journey into the bizarre, we must first step through the quantum looking glass. Quantum mechanics, the physics of the very small, is not merely strange. It is, as physicist Richard Feynman famously warned, impossible to understand in any conventional sense. We can only accept its mathematical validity while our minds reel at its implications. At the quantum scale, particles exist as probability waves until measured. They can tunnel through impenetrable barriers. They can influence each other instantaneously across vast distances in apparent violation of the cosmic speed limit, the speed of light. The cornerstone of quantum weirdness is superposition, the ghostly ability of particles to exist in multiple states simultaneously. An electron can spin up and down at once. A photon can take multiple paths through space concurrently. This isn't merely theoretical. The double-slit experiment reveals particles passing through two openings simultaneously, creating interference patterns with themselves. Yet when observed, this wave-like behavior collapses into particle-like precision. The very act of measurement forces reality to choose a single path from infinite possibilities. Even more unsettling is Heisenberg's uncertainty principle. It's not simply that we lack the tools to measure precisely. The universe fundamentally prohibits perfect knowledge of certain paired properties. The more precisely we measure a particle's position, the more unknowable its momentum becomes. This isn't a technological limitation, but an intrinsic feature of reality itself. And then there's quantum entanglement, what Einstein called spooky action at a distance. Two particles, once entangled, maintain an instantaneous connection regardless of separation. Measure one, and its partner responds instantly, even if separated by galaxies. This phenomenon has been repeatedly verified experimentally, yet defies our understanding of causality and space. But these quantum peculiarities are merely the gateway to even stranger theoretical landscapes. Consider the many worlds interpretation proposed by Hugh Everett in 1957. According to this theory, every quantum event, every fork in the probabilistic road, doesn't just select one outcome. Instead, reality branches into multiple universes, each containing one possible outcome. Think about it. When Schrödinger's cat faces its quantum fate, the universe splits. In one branch, the cat lives, in another, it dies. Both realities exist simultaneously, just in separate universal branches that can never communicate. This isn't science fiction. It's a straightforward reading of quantum mathematics without the artificial collapse of probability waves. If true, an infinite number of you exists across the multiverse, each making slightly different choices, living slightly different lives. Every quantum possibility becomes reality somewhere. The many worlds theory elegantly solves certain quantum paradoxes, but at an extraordinary conceptual cost, infinitely branching realities that multiply with every quantum event in the universe. Some physicists embrace this interpretation precisely because it takes quantum equations at face value without requiring additional mechanisms to explain measurement. Now let's unravel another cosmic mystery: string theory. For decades, physicists have sought a theory of everything that unifies all fundamental forces. String theory proposes a radical solution. What if particles aren't point-like dots, but tiny, vibrating strings? Different vibration patterns produce different particles, just as different vibrations on a violin string produce different notes. These fundamental strings are inconceivably small, approximately 10 meters, a million billion times smaller than a proton. But here's where string theory becomes truly baffling. These strings require additional spatial dimensions to vibrate properly. Not just the familiar 3 dimensions of space plus time, but 10 or 11 dimensions in total. Where are these extra dimensions? They're all around us, curled up so tightly at every point in space that they remain invisible to our perception. Each point in our universe contains these hidden dimensions, folded into complex geometrical shapes called Calabi-Yau manifolds. The specific configuration of these extra dimensions determines the physical laws that govern our universe. The mathematical beauty of string theory is undeniable, but its greatest challenge remains experimental verification. The energies required to directly observe string effects far exceed our technological capabilities. Critics argue that without testable predictions, string theory remains mathematical philosophy rather than empirical science. Yet its proponents point to its elegant unification of quantum mechanics and gravity, 2 frameworks that have stubbornly resisted reconciliation by any other means. The quest continues to find observable consequences that might confirm or refute this strange, multidimensional vision of reality. Perhaps even more mind-bending is the holographic principle. Inspired by black hole physics, it suggests that our 3-dimensional reality may be an illusion, a projection from information encoded on a distant 2-dimensional surface, much like a hologram projects 3D images from a 2D film. This idea emerged from studies of black hole entropy. Physicist Jacob Bekenstein realized that a black hole's information content scales not with its volume, but with its surface area. Leonard Susskind and Gerard Hooft extended this principle to suggest that the entire universe might operate this way. All the information describing our 3D world could be encoded on a 2D boundary. If true, the holographic principle completely transforms our understanding of space itself. The third dimension we experience would be emergent rather than fundamental, a projection of more basic information stored elsewhere. Everything you perceive as depth and volume would be a sophisticated encoding of information on a cosmic screen at the edge of the universe. Some researchers see evidence for this principle in certain quantum field theories that demonstrate equivalence between systems of different dimensions. The AD-SCFT correspondence in string theory provides a mathematical framework that supports this bizarre possibility. And then there's perhaps the most philosophically disturbing theory of all, simulation theory. What if our entire reality is a sophisticated computer simulation created by an advanced civilization? Oxford philosopher Nick Bostrom formalized this idea, arguing that if advanced civilizations can create detailed simulations of conscious beings, and if they would create many such simulations, then statistically speaking, most conscious beings would be simulated rather than real. By sheer probability, we are more likely to be simulations than biological entities in a base reality. Some physicists, including James Gates, have found what appear to be error-correcting codes, similar to those used in computer programming, embedded within the equations of string theory. While far from conclusive, such findings fuel speculation that our reality might contain computational artifacts. Others suggest that the quantized nature of reality at small scales resembles the pixels in a digital simulation, and that the cosmic speed limit of light could be analogous to a processing constraint in a vast computational system. The simulation hypothesis remains unfalsifiable with our current understanding, yet it haunts our conception of reality. Finally, let's confront our most intuitive assumption, the nature of time itself. The block universe theory, supported by Einstein's relativity, suggests that past, present, and future all exist simultaneously in a 4-dimensional block of spacetime. Our perception of flowing time is merely an illusion created by our consciousness moving through this static reality. Even more radical are theories of retrocausality, where effects can precede causes under certain quantum frameworks. Some physicists propose that time itself may not be fundamental, but emergent, a secondary phenomenon arising from quantum entanglement between particles, with no privileged direction. As we conclude our expedition through these strange territories of theoretical physics, we're left with more questions than answers. We stand at the edge of human understanding, peering into abysses of complexity that challenge not just our knowledge, but the very nature of knowledge itself. These theories remind us that the universe is under no obligation to conform to our intuition. The cosmos may be not only stranger than we imagine, but stranger than we can imagine. Our evolved brains, optimized for survival on the African savanna, now strain to comprehend quantum realms and higher dimensions. What unites these bizarre theories is their mathematical consistency. Despite their conceptual strangeness, their equations produce verifiable predictions. When mathematics leads physicists into such conceptually challenging territory, should we trust the math or our intuition? Perhaps the strangest aspect of modern physics isn't any particular theory, but the humbling recognition of our cognitive limitations. We pursue understanding with tools never designed for such tasks, like trying to map the ocean floor with a ruler. Until next time, remember that in the quest to understand reality, the horizon of knowledge only reveals more horizon. Thank you for joining me on this journey through the strangest theories in physics.